This is a lesson in freefall motion in the kinematics unit. We've covered several important concepts before this point, including the idea of acceleration and constant acceleration, and the kinematics equations that are associated with any object moving at constant acceleration. Free fall motion is a special case of 1D constant acceleration motion. It's like a subset, and it's a nice concept to practice with. Free fall motion, and remember there was Newton in his orchard with his bird, and he saw an apple fall, and he said gravity, right? Gravity's pulling down all the time. All the time. And what we're going to assume, and if you think about that apple there, we're going to assume no other forces. Right? Because I know you're thinking in your head, like, what about the force of the tree? Or what's the force of the ground? Or the wind? Or etc. What we're thinking about is just an object in the air without anything else touching it and without any external other forces going on. It's just simple gravity, one force acting on this object. And so we're looking at it after leaving whatever it was on in order to gain a free fall motion, whether it was a hand or what have you. It's after leaving that and before touching the receiving object, whether it's the ground or a target or water or whatever. So nothing's touching it. It's after it's been thrown, after it's left, and before it's touched that whole time. All right. Falling objects then experience an acceleration due only to the force of gravity in that time. The acceleration is downward. Remember, acceleration is a vector. So we have to think magnitude and direction. It's downward at all times. Also, it is the value, and note that this is SI units, 9.8. Some textbooks will use 9.81 meters per second squared, and those are the units of acceleration. That's the magnitude. It's an acceleration in the y direction, and so you'll see the subscript y being used with this. Okay. I'm not going to call it negative because remember, I could make upward the positive y direction, or I can make downward the positive y direction. If downward is the positive y direction and the acceleration vector is downward, then I would have a positive acceleration vector. Okay, so that's why I didn't put a negative sign in here. So it depends on your coordinate system what the sign is on this. Okay, and what you will see is because the object is accelerating, it will be able to cover, and this is the distance in meters. It starts at 10 meters. If I drop an object, it will start gaining speed and be able to cover more distance in the same amount of time. In this picture, every dot represents 1 second in between, and you can see between 1 second and 2 seconds, in the second it travels faster. In this second, it travels faster than the prior second because it's accelerating. And what I'm going to note here, and I found this, students have this, it gets confusing about what free fall is, right? Because you see free fall and you're like, okay, it's free. It's a free object. But the falling part is a little weird because we're going to make upward motion is still technically defined as free fall motion. And we go back to the technical definition of this. What's going on here is that there's only the force of gravity. So whether the object is moving upward or the object is moving downward, gravity is the only force, and therefore it falls in the category of free fall motion with just acceleration, even though it's moving upward. I know it's weird that it's falling and it's moving upward. Okay, the acceleration is still downward, and eventually it will be overcome and move downward. And that's how we can still say it's like falling. The equations for kinematics under free fall motion are very similar, exactly the ones that we developed for 1D motion under constant acceleration, right? The acceleration is a constant value at all times. So the kinematics equations apply, and we're simply replacing y with x in them, right? Any place where you see position, it is a y value, and all of the velocities and accelerations are also in the y direction. We're thinking only vertically. A few special properties about free fall motion that we need to be aware of as we move forward. The first special property over and over again so far is that the acceleration is 9.8 downward at all times. Okay. Another thing that happens is because the acceleration is constant, then the velocity is constantly changing. As we move upward, if I throw an object in the air, as we move upward, the initial velocity is so long, and we know that it will get smaller as it moves towards the top. When it reaches the top, let's say it goes 10 meters up, when it reaches the top, up at that top there, at the top, the velocity is 0. It slows all the way down, it'll come to 0, and then it'll start increasing downward again. So as it moves downward, it will speed up. And so the velocity vectors will be symmetric. Remember, this results from with a parabolic motion at the top. All right, the velocity is 0 there, and the velocity is decreasing as it moves up and increasing as it moves down, and it's symmetric. It has that line of symmetry in here, right? This axis of symmetry. So whatever it is at one point, it must have been at the other point. I wanted to cover graphs for 1D motion because they can be confusing. The acceleration one is the easiest one to start out with. It's a constant value, 9.8, and you can see if we assign upward as positive, then 9.8 is right above negative 10, negative 9.8. It's a constant value. It's downward, this value at all times, and it's a very simple graph. It's a constant value. Moving towards the velocity graph, we can see that the slope, remember the acceleration is the slope, and the slope of the line is constant, right? Y equals mx plus b. I have an acceleration. As long as I have upward defined as positive, I have negative 9.8 meters per second squared in here, and you can see that corresponds to the slope of this line. It's a negative value. It is a constant negative value. And this is where I've seen students struggle with the concept here, is that this is a constantly decreasing line. It looks like it's getting smaller the whole time. And I agree, it's getting more negative. But as something gets more negative, the magnitude increases. So we're increasing with speed. We can note that it starts at 20 meters per second, which is a positive value. It starts with positive 20. And as the object reaches the top, right, at this point here, this will be the top, when the velocity at the top equals 0. So in this region up here, it's moving upward and it's slowing down. Notice that it decreases in value, 20, 10, 5, down to 0. So it's slowing down up here. This is the top, so this must be the downward motion. And in this region, we know it has to be speeding up. And remember, speeding up means that the velocity vector is getting larger, okay? It just so happens that in this region, the velocity vector is in the negative direction, right? Here's negative 5, here's negative 10. It's getting larger in the negative direction. It's getting more negative. Upward motion is still free fall, and our graph exhibits that. It is a constant graph. There's no discontinuity in here. The graph for the upward motion is continuous right into the downward motion, coming from the fact that the acceleration is 9.8 downward at all time. And that's why we call upward is still falling, because it still falls within this technical definition of only gravity is acting and the acceleration is 9.8 gravity downward. As we look at the position versus time graph for free fall motion, we know the equation of motion, and it is a parabola. We also know that the acceleration is negative 9.8 meters per second squared, so we get a downward pointing parabola. We're familiar with the idea that it reaches a maximum value, right? Y max, and that is at the top. So the time it takes to get to the top is here. It returns back to its beginning position at twice the time it takes to get to the top. As long as it's symmetric, it should do that. What we're going to know is that the velocity is the tangent line to the position versus time graph. Just like the slope relates to the velocity graph relates to the position graph. How is that true? Well, when I look at and overlay these graphs, here's the acceleration graph, constant value, a negative value. The velocity graph we were just looking at is right here. We know that this is the top, this is the beginning time, and this is the end time. It goes up to the top, falls down. All right. And so the acceleration is the slope of the velocity. Well, the tangent line to the position graph is the velocity. So when I think about the tangent line along here, it's steep to begin with, which corresponds to a large value. But as I move along this graph and towards the top, the value gets smaller and smaller. And at the top, the tangent line is perpendicular or tangent to, right? And at the top, the tangent line is flat. There's no slope there, corresponding to a zero velocity at the top. Note that it has an acceleration the whole entire time, regardless what the velocity is, regardless what's happening in the motion. The acceleration is a constant value the whole time. After the top, the object starts moving downward, and we can see that the slope becomes steeper, and that corresponds to a larger value in the velocity. Remember, it's more negative. It's a larger value. So that's sort of how to think about these quantities all together and how their graphs relate to one another. I have a challenge here. What is the simple difference made to create the graphs to the right compared to the previous graphs below? These are down here. These are the graphs on the previous slide. And how they compare to this graph, it was changed. There's a simple difference. I'm going to start with acceleration. Notice the acceleration is negative 9.8 here and it's positive here. So it seems like there's just a negative positive thing. It's the same parabola but pointing the opposite direction. It's the same line but with a positive slope rather than a negative slope. And it seems like what was done, this is a simple change, is that downward was defined as positive y rather than upward. So when the object moves away from the ground, it will be moving in the negative direction. It started with a negative velocity away from the ground and then falls towards it in the same direction of the acceleration downward. It doesn't matter whether you have upward or downward defined as positive as long as you're consistent in those assignments, in your word problems and solving your problems in the graphs with your vectors, etc. The example problem I picked is pretty straightforward and typical. The example problem I picked is very typical for this type of material for 1D constant acceleration and with free fall. We're asked several parts here. We can see that there's 3 parts. And I'm going to read it so we can get established in the problem. Alex jumps straight up from a diving board and dives feet first into a pool. They start with a velocity of 4.15 meters per second and their takeoff is 1.75 meters above the pool. How long are their feet in the air? What is the highest point their feet reach above the pool? What is their feet's velocity upon hitting the water? Okay, so I'm going to draw a quick position versus time graph over here. Just a quick one here to get an idea of what's going on. There's a time here and there's a position here. It seems like they have initial position, 1.75. I can draw that on here, 1.75. They're moving upward and they're going to reach a maximum height and then they're going to fall down to the water. So there's some point up top where they're at the top, and I'll call this T top, and this is the end, right? Maybe I'll call this T final. Up top here, they reach some maximum height. I'm going to call this Y max. And at that point, we're going to note that the velocity at the top equals 0. So I'm kind of just noting that. I'm going to keep that in mind. It's not stated in the problem anywhere, but it's one of those things that we will remember that we know. Another thing I'm going to note is that the acceleration is 9.8 downward the whole time. Okay, so we're sort of encoding the problem, and this is just a drawing. Some people are comfortable writing a drawing first. I'm going to identify the variables again over here. We have an initial velocity of 4.15 meters per second. We have an initial position of 1.75 meters. There's an acceleration of negative 9.8 meters per second squared downward. I don't know any times. I know the velocity at the top is 0. V top equals 0. How long are their feet in the air? I guess I know another thing. When I'm thinking about things that I know, when I think about the feet being in the air, at some point they're not in the air anymore, which means they hit the water. And when the feet hit the water, their position is 0. I've defined 0 to be the surface of the water. So y equals 0. So when I think of the position here, I can say y final equals 0. That's something else I know. So I'm just writing stuff out, things I know implicitly, and also things that are directly stated in the problem. The first one asks for how long are their feet in the air. That is a time. And I don't know the final velocity here. So any equation, including the final velocity, is going to be useless to me. So the only equation that's really going to work for me for part A is y final equals y initial plus v initial t plus 1/2 at squared. So I'm going to write that out and fill in the parts. Y final, I know to be 0. Y initial, I know is 1.75. The initial speed was an upward, a positive 4.15, and then the t variable is in there. I don't know time. I'm trying to solve for it. It's like t final. I can write a tf in there. Plus 1/2, the acceleration is negative 9.8 t final squared. So we're going to solve for that t final. You can note that this is a quadratic equation. You can make it a little bit nicer if you like. Plus 4.15t minus 4.9t squared. Use any calculator for solving the quadratic that you like. And when you solve this, we're going to note that there's two solutions, right? There's this positive time over here, and there's a negative time. You'll get a negative time because it's a quadratic. You should expect a parabola to intersect the 0 twice, but we really care only about the last one. And so when you solve this and get that positive time out of it, you will get 1.15591 seconds. And if we're looking at significant figures, we want 3 significant figures, so we might just round it off at 1.16 seconds. I guess that seems okay. If you've jumped into a pool from a diving board, it seems like it's quicker than 1.16 seconds, but it seems in the right range. It's not 100 seconds. It shouldn't take that long to go up and over. And it's not like a third of a second where it's like instantly happening. It takes some time to go up and come back down. So there's the answer for part A. Did that. B, what is the highest point their feet reach above the pool? So it seems to me they're asking what is y max? What is y max? So I'm going to have to find an equation up here that relates the initial and final positions. I know at the top, another thing that I can use at the top is the fact that the velocity is 0 up there. V final is 0. So when I'm looking at the equations, V final is here. It includes the displacement, and it doesn't have the time. I don't care about the time. I'm just asked for how far does it go up, and I know the final velocity. So I'm going to write this down. V final squared equals V initial squared plus 2a delta y. And I'm going to note over here that delta y equals y final minus y initial. We can find some displacement it goes in order to reach the top, but we have to take into account that it started at 1.75 meters above the water if we want to know how high the feet are above the pool total. So I'm going to solve this equation for delta y, do some algebra real quick here. Solve algebraically before I plug in the numbers, and I'm going to plug in the numbers here. The final velocity is 0. The initial is 4.15, and I'm going to put parentheses around that. And then the acceleration is negative 9.8. It's important to have that negative sign so that there's a negative on top and a negative on bottom. Overall, this becomes a positive value, and it is 0.8787 meters. To finish solving, I'm going to note that y final equals y initial plus delta y. Right? If I do algebra on that equation, I can figure that out. So I have 1.75 plus 0.8787, which results in 2.6287 meters. That is the final height. Y final is that height above the pool. As I'm working this, I note that it may have been your first inclination on part A to find this value first, like to divide the motion up. And the powerful move that I did in solving part A was remembering that the final height is 0, and that lets me solve. I don't need to divide it up into two parts. This equation representing a parabola, if I solve it for where it hits these axes, I don't have to take into account the motion in between. The math knows it happens, but it doesn't matter. We don't have to consider it. All we have to do is consider the initial and final point with the information that we're given. So it reaches 2.62 with 3 significant figures. I suppose we could round it to 2.63, and that would be a more proper answer. The final part here, C, what is their feet's velocity upon hitting the water? So we actually want to find V final. And this is for the whole entire time, so we actually know the time it takes to get to the water again. So if I think about the equations that have V final in them, this one seems the easiest. I can plug in 4.15. I have a negative 9.8 meters per second downward, meters per second squared, and the time was 1.1, and I'm going to hold some sig figs here just to keep it accurate. And the final velocity, when you calculate this, is negative 7.1779 meters per second. Does it make sense that it's negative? You may say that looks weird because it's negative. We threw out the negative time, but we keep a negative velocity. Yes, when we think about when the diver reaches the end of the motion, they're moving downward, which corresponds to a negative velocity. So that's an okay value.